Okay, in this tutorial, we're going over week 4 case study continued. Um, we're going to continue the case study for the bridge design, and here I'm going to open up these links one by one. We also went over the different types of bridges, and so here's what we're going to do. We added more things from here. I uploaded a bunch of pictures, and we'll talk about that when I bring up the case study. But first, the different types of bridges. Definitely want students to go over this. First bridges were, when they were done, they were pretty much, trees that fell over like small creeks, and that's pretty much where the ideas came. It evolved eventually to multiple logs to have people travel over bodies of water. And designs of bridges vary depending on the function of the bridge. I thought this was a cool picture because I'd never seen a bridge carry a boat before, but there we go. Apparently that's a thing. But these are more common bridges that we see daily. So here are the different bridge types. You might want to note these down for when you do design your bridges. So there's the arch, beam and truss, there's cantilever, suspension, and cable stay. So we'll go over these real quickly. And so the arch bridge typically was conceived in the Middle Ages, and they were made out of stone, quarried from a local mountain, so basically carved out of a mountain piece by piece. They took forever to make, and they really don't have a long span, so you need multiple arches for a very short bridge. As technology grew in construction and the different materials that we have readily available, we still use the arch in a lot of our designs because the arch is really, really strong. It's one of the strongest engineering components and architectural features that was ever invented. And so the bridge, the arc on the bridge is always under compression. So you can imagine if there was a truck right here, this deck right here would want to bend down, and because of the amount of weight, but due to the arch in place, in engineering, the idea is to transfer the weight evenly throughout all the material, so that not one piece of material, not one cross beam, or is experiencing the entire load of whatever's on top of the bridge, because that's how failures happen. And so the idea is to transfer the load evenly, not just to one side, but both sides evenly. And so the bridge is always under compression due to the weight of the materials of the bridge itself and whatever traffic, whether it be pedestrian or vehicles, traffic, trucks, cars, motorcycles, bicycles, all the above. Could be a train. All right. And so here's the different parts of, the arch bridge, the modern art bridge. You have your supports on either side. You have the deck that go all the way across. You have your main arch, and you have your suspension cables. The wind bracing as well to connect both of the arches. So you have one arch on one side, one arch on the other side. And then you have these wind bracing material to help brace the arches. So when the wind comes, they're not going to fall over. So you can see if there was a load right here, if there was a truck right here, this deck would want to go down. But what prevents it from going down is the cable that's connected here. It's anchored here and up here on the arch. And the arch is being pulled down. Essentially, the load from here is being transferred to up here, and so the weight of the truck gets transferred down into the supports evenly, and that's how this bridge works. You can see that, and this is one of the first arches that were conceived of. The Middle Age people, the people of the Middle Ages discovered that through this arch, it can handle a much greater load than any other device out there. And one key component to making this all work is this stone right here. This is called the Keystone. That's easily removed, and once that's removed, this all comes crashing down. So the only thing that's really holding this together is the weight of the stones itself. There's no cement gluing these together type thing. It's just the weight of the stones that are really pushing it all down, and that's why these structures are always in a constant state of compression, because once it loses compression, these come crashing down. So, and you saw in one of the first bridges there was, two arches to create that bridge, but they all share the same responsibilities, transferring the load of the bridge. And anytime you hear the word load, it just means weight of the bridge itself and anything that's crossing. Okay, here's some different types of arch bridges. You can pause the video and go ahead and read these. This is a bow bridge, bow arch, because it looks like a bow from a bow and arrow. And then you got triple joint, arch bridge without joint, and then double arch bridge. Okay, so this is we're going over the bridge, beam bridge and truss bridge. So this is the beam bridge that we see daily in LA. Our freeways are made like this. They're also called girder bridges. They're the simplest kind of bridge. There's nothing fancy about them. They do one job, and then they get things transported over them. So there you have it. And here are some truss bridges. This is considered a truss. On one side, you'll have this shape, and it will make up the sides of the bridge. And then across, you'll have the wind beams. And then you have the deck. And that's it. You don't really use these a whole lot anymore for long span bridges. So if the bridge is really long, these aren't used for that anymore. We use other materials for that. But these are relatively expensive if you do a long one, a long bridge. But if you do just a short little one over a creek like this, they're not that bad. And so that's what we mainly use them for now, is just short span bridges. And you can see here where the arrows, again, engineering, we just distribute the weight down to the supports that are anchored on either side. And so that's what a truss does. Okay. And so here's a timber truss, and anytime you see the word timber, they're talking about wood. And then this is a steel truss bridge. This is a cantilever bridge. Cantilever systems are developed by, let's see if I could draw it right here. So if you have a cantilever, let's just say this is a column here, this is a column here, and let's just say we're trying to make a balcony. And in order to make a balcony, oops, let's undo that. So anyway, in order to make a balcony, so you have to have a column of some sort, and I'm drawing this super fast and it looks really ugly. My apologies, but you can get the basic idea. So if we're going to do a balcony, there's nothing underneath here. You can see how if we don't anchor this balcony to this these posts here and here, this beam right here will fall right over if any amount of weight is applied to it. And so that's all cantilever is to make sure that the weight, any type of weight, amount of weight that's going to be experienced on this material over here that's hanging beyond this post is going to be able to handle it by being offset by the amount of material on this other side, and it's anchored to other posts. And then this actually might go even further than that. So this might actually go out here, and there's another post. So it really depends on the engineer and what the engineer decides. And so this is the cantilever system, and it just means that there's going to be enough to where that's not supported. And that's what's going on right here. They created this cantilever system that transfers the weight all the way down to the supports. And these are the supports right here. There's 4 columns going down all the way beyond the bottom of the river and into probably bedrock. And so you have this kind of floating thing right here. That's similar to this balcony, and you have it on both sides. And you hardly see these in the United States, but you do see these in Asia, and that's pretty much how their engineers solved a lot of these problems that they do have. And so there's that. There's just some of the joints that have been used, and then this is the transfer of the weight. And here's some of those cantilever bridges. And then you have suspension bridges. Suspension bridges started out with the rope and wood planks. And you may have seen these in the movies where people are hesitant to cross these old rope and wood plank bridges because they're afraid that if they step on one, and they always fall through in every single movie. Yeah, that's pretty much how we got the idea from the suspension bridges. But it wasn't really feasible until this gentleman right here, Albert Rupp, created the steel cable. And what you see here is the main cable. Let me see if I can highlight that a little bit. So right here you see the main cable, and they go across like that. And then you see the suspension cables all coming down off of the main cable, like so. And I'm drawing very, very crooked, but you can kind of see the cables in between those lines. And that's pretty much how a suspension bridge is created. You have these towers right here. So here are your towers. These are your supports on both sides. And these will hold up all the cables. And then here's your deck. Now your deck is made out of concrete and rebar. And all the weight's being transferred over to the towers. And that you have this tremendous span capability. This covers the entire portion of the river and then some, because this one goes way out to there. And so that's what's great about the suspension bridge. And here's the suspension cables. It's basically metal rope, and it's super, super strong. And this is one of the most famous suspension bridges here in California. If you've ever been to the Bay Area, there you are. Fun fact, there's a lot of maintenance that goes on. Every year they start on one side, and at the end of the year they paint this entire thing. And then they start over. So every year they paint this over and over again. That salt water right there, that salt water is going to eat up all this metal, so they have to maintain it by painting it every year. And if you've ever crossed this bridge, there's a toll going one way and another toll going the other way. And that's how they pay for the painting of this bridge. And so, and not to say that other bridges don't need maintenance. Other bridges do need maintenance. Same thing. And so here's some of the parts that I already talked about. There's on the ends, there's anchor blocks, so the main cable can anchor to the anchor blocks, as well as anchor to the towers. And then you have the suspension cables, you have your deck, and that's pretty much it. You have your towers. Okay, so this is a cable stay. It's very similar to suspension cable, suspension bridge. The only thing is you don't have a main cable. If you look at this, there is no main cable going this way, this way, and this way. Oop, let me undo that. Reset. Like the bridge in San Francisco. So it doesn't do this. Instead, it does what it does the cables like this. And it kind of just fans it out on both sides, so this side as well. And so I'm not going to draw all of them, but you get the idea. And it's just, the parts are really, really simple. You have two towers and then just the suspension cables, and that's what holds up this bridge. And it's very effective. So you have, again, here's the parts, here's the foundation. You can kind of see how far the foundation goes down to bedrock. You have the tower, the roadway, and then the cables. And it's basically like a canopy of cables going over the road. And you have the harp design, and you have the fan design. It really depends on what the architect and engineer decide on the design. And there you have it. That is the cable stay bridge. So in the case study, this is what it should look like. What we've done so far. I've uploaded these pictures, so go ahead and create these files. And I don't know why this messed up when I uploaded this, but it did. So let's go over here. It should look like we added more for week 4. So in week 3 and 4 we did, here we go. So we did this bridge type, bridge crossing, and bridge load. We watched a video on this. I posted up the video, show you exactly where that's at. And we started right here, site location. And we added these as well. These are elevations. I drew this up in SketchUp, and this elevation. And that's pretty much what we did in week 4. We also watched this video right here. This is in week 3. So what you see in week 4 is a combination of week 3 and week 4. And when you're done with it, turn it both into week 3 and week 4 so I can grade it. But this is the video that you watch, and it's located in week 3. I'll go ahead and put that in. It's still in week 3, so go ahead and open up week 3, watch this video, and that's pretty much how we got these design factors. We took these notes from that video. And that's it. We'll get into more of these later on. Oh, we did add the 6th Street Bridge, and so if you want to go to week 4, we did look up the 6th Street Bridge. So this article, and then we just went on to Google, and we found out that this gentleman right here, you can pause the video and go ahead and take a look at what this slide should entail. He was the architect for the 6th Street Bridge here in downtown LA. Now it's still being built, so we got a little background history of it. Again, pause the video. This is the original bridge. It was demolished we call it demoed, a few years back, and now they're starting to build it, and it's going to look like this when it's all said and done by the end of this summer. Then we got here some architectural features. So there's 10 pairs of these arches, and that's pretty much where we stopped. We'll get to these later, but if you want to stop the video and go ahead and make them, you're welcome to. Those are just more factors for the Pasadena Bridge that we are going to redesign. And that's it. That's week 4. So when you're done with week 4, go ahead and download it into PDF and submit it both into week 4 and week 3.